Testing, audio test. Okay, fantastic. Alright, hello everyone. And today we are beginning the fourth video, the fourth part of this secondary 3 AMath topics crash course. So for today, the focus will be on polynomial functions as well as how to perform basic partial fraction decomposition. As usual, make sure you have your notes with you. We will be going reasonably quickly, I would say. Right, so for today, we will be looking at polynomials and partial fractions. Now, first of all, one thing that I want to very quickly set the ground for and just declare is that as far as the content today goes, I will not be focusing too much in terms of, for example, the very basics where we are adding together terms. I feel like there is little need for that. So you will see me essentially touch and go for the first few portions. Right? I will leave you to read on them in your own time. Okay, so let's begin. First of all, we need to, of course, understand what the word polynomial means. It simply is a collection of algebra objects that take this shape. A number, a, any number, multiplied by the algebra x to the power of some certain power, for example 1, 2, 3, 0. And then we will have all these different combinations added together with either a plus or a minus. The criteria is that the number in front, a, has to be a real number, and that the power of the algebra n must be a non-negative integer. So in this case, we have the whole numbers, and in that case, you have anything really. Right? So some simple examples are given over here. If, for example, you see that a function contains a square root, then we instantly know that this guy over here is going to be power half. And that wouldn't make sense anymore. It will not be a polynomial because half is not even an integer in the first place. Right? As for real numbers, if you recall from the very first video of the series, real numbers will mean that, as far as our syllabus goes, it is a number that you can obtain in your scientific calculator. Right? So for numbers such as the square root of -1, that will be a no-go. For numbers such as taking the real valued logarithm of -2, that will be a no-go. So if you see all these funny objects that give you a math error, then we will recognize that these things are not real numbers, and therefore these algebras, these functions, are not polynomials. You are not real. Yeah, a bit of a meme. Okay, anyway, let us move back to the not to this image. Let us move back to the notes. Right? So as a reminder, functional notation, fx, gx, gamma x, so on and so forth, it over here it does not mean f multiplied by x. That is incorrect. It simply means that f is the name of the algebra and x is the input that is going in. Of course, we have already covered this previously, so I am not going to waste time on this. Now, as far as polynomials go, they will follow your basic algebra rules. Addition and subtraction follows like terms. In other words, if I have 2x3 plus 4x3, I get 6x3. And if I get 2x3 plus 2x2, well, you can't do anything with that. At most, you can factorize. Right? This is very straightforward. I will leave you to review this on your own. Similarly, multiplication will be the same algebraic rules as always. We will treat it with the rainbow opening method, right? The rainbow expansion. For example, if I have fx multiplied by gx over here, we recognize this as fx like that multiplied by gx like this. And when we are opening this up, it is simple enough for us to simply map everything one at a time. So in this case, we will have 6x cubed multiplied by 3x, that will be 18x power 4. And afterwards, negative 2 multiplied by 6x cubed minus 12x cubed. And then from here, you can continue to work everything out accordingly. Right? And afterwards, you can go on to simplify. So this is also very straightforward. I do not have much to talk about. The next thing I want to talk about is polynomial division. Now this is a lot more important, and doubtless some of you who are watching this video to prepare for Sec 4 would have forgotten the processes required in order to perform this particular procedure. So allow me to very quickly review what we need to do with this particular example in the notes over here. So they have told us that we have this quadratic 3x squared minus 2x plus 5 divided by the linear polynomial x plus 2. So in order for us to perform this division, what we need to recognize is that for long division of polynomials, we will always focus on the first term of whoever is being attacked, the first term. Later on, it will be the first term as well. And even when we're looking at the person doing the dividing, it will be the first term who is the most important. So the first term will be labeled, or rather indicated with the red color. Right, so we start by taking first divided by first. In this case, we have the first term, 3x squared, divided by the first term, x. Clearly, this will give us 3x, which is why we write the 3x on top. Right, the answer to the division will be on top. Once we have written down the answer, the next thing we need to do is we will need to take this answer, 3x, and multiply it by whomever we were performing division with, in this case, x plus 2. This will give us 3x squared plus, let's see, plus 6x. And this 3x squared plus 6x, right, we're going to put him underneath, and we're going to do subtraction from the original object. The reason why we do subtraction is actually somewhat straightforward. You can actually imagine this happening with your normal numbers as well. For example, if I have 582 divided by 2, we will start with the first digit 5. 5 divided by 2 gives me 2 with a remainder of 1. Doesn't matter. We will take this number on top 2 and multiply with the person we were dividing with. Then we will minus. So this will give us 5 minus 2 times 2, 5 minus 4, 1. Afterwards, the 8, 2 will go down, and then we can continue the long division. In this case, we'll have 9, 2 times 9, which will give us 18. Our minus 18, this will give us 2. And then from here, 2 divided by 2 gives us 1. And we are done. We'll get 291 as the answer. So even with our actual numbers, the process is the same. Right? So to recap, always focus on the first object. Both the person who is dividing and the person who is being divided. Once you focus on the first object and you recognize who is the result obtained from the division, write this result on top, and then take this result and multiply it by the person who is doing the dividing. No. The person who is doing the dividing over here. Then we will subtract using this result. Once this is done, then you will be able to get a new result. In this case, the new result is over here, right? Negative 8x plus 5. And once we are here, you will repeat the process. Look at the first object outside, divide, minus away what you get after multiplying with the person doing the dividing, so on and so forth. Keep repeating this until no more division is possible. So in this case, we have negative 8x, we have x. Division over here clearly is going to give us negative 8. So I'll write this negative 8 on top. There afterwards, I'm going to take negative 8 multiplied by the person doing the dividing, x plus 2. This will give us negative 8x minus 16, which I will write on the bottom. And then we will do subtraction from the existing result. And this will give us the next step. Of course, in this case, once we are in the next step, which is 21, then you will see that 21 itself is degree 0, right? 21 equals to 21x to the power of 0. And x to the power of 0, you cannot divide by x to the power of 1. It's not happening. Therefore, what we will do is, there is no more division that can be done. We will end our work over here. So allow me to go through a few more examples, right? I will leave the first example as an exercise for you to do. Let's take a look at the second one. We are given 6x cubed minus x squared minus 5x minus 1 divided by 2x minus 1. Alright, so first step, we're going to look at the first object. And this will give us 6x cubed divided by 2x, which is cancel, 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 which is 3x squared. So I'm going to write 3x squared on top. There afterwards, I'll take this 3x squared and multiply by the person doing the dividing, which is 2x minus 1. This gives us 6x cubed minus 3x squared. So I'll write 6x cubed minus 3x squared below, and we will subtract. Once this is done, then we will end up with 2x squared minus 5x plus minus 1, like so. Right? As a general guideline, the current existing first term, in this case x cubed, should completely disappear by the time you are done. If for some reason you perform the minus, the subtraction, and it still hasn't disappeared yet, the object in front hasn't disappeared yet, then you know for a fact that something must have cocked up. Right? So once we are here, let us continue. We're going to look at the first person here, 2x. Look at the first person there, 2x squared. This division is definitely going to give us x, positive x rather. So after that, I'll take positive x multiplied by 2x minus 1. This gives us 2x squared minus x. And then we will subtract again. In this case, we'll get negative 4x minus 1. Last but not least, negative 4x. We'll look at the first object yet again, right? Which will be 2x over here and negative 4x over there. And this division is going to give us negative 2. So I'm going to write negative 2 over here. I'll take negative 2 and multiply by 2x minus 1, which will give us the following. Once we are here, do a subtraction, and then we will end up with the final result of negative 3 as the remainder. And therefore, I will say that, let's see, I will say that my polynomial 6x cubed minus x squared minus 5x minus 1, the numerator is actually equal to the quotient, 3x squared plus x minus 2, plus the remainder, negative 3, multiplied by, multiplied by the, oh wait, sorry, my mistake. We will say that it is equal to the quotient, multiplied by whomever was doing the dividing, plus the remainder, which in this case is minus 3. The reason this makes sense is because we will simply be able to rearrange this, right? I can simply rearrange this by putting 2x minus 1 as the denominator. When I fix this as the denominator, the right hand side very clearly will see a cancellation here to get 3x squared plus x minus 2. And over here, there is no cancellation, so he will remain as the numerator and the denominator stays there. Right? So in either case, this is the quotient. And that is the remainder. Just as how if I have 7 divided by 3, I'm going to have 2 remainder 1. and therefore 7 can be written as 2, the quotient, multiplied by 3, the person doing the dividing, plus 1, the remainder. The remainder is the one who is excluded, right? He is the one who does not get to join the party. Right? So if you're okay with this, I will perform one more worked exercise for you. Let's look at the third problem on this page. Over here we have some real big numbers, right? I have x squared minus x plus 1 as the dividing person, and the person being divided is degree 5, right? Degree being the word that means the highest power inside the algebra. So we have degree 5, and that gives us this extremely gigantic piece of work over here. So let's begin dividing. We'll look at the first object, 2x5, the first object, x2. The division obviously gives us 2x cubed. From here, I'll take 2x cubed multiplied by x squared minus x plus 1, which, if you work it out, will give you the following. Once we obtain this, we will subtract. Be careful of all of the double negatives, right? Make sure that you are not clowning around when you actually perform the subtraction, because it would be a little bit embarrassing to make a mistake here, not gonna lie. Right? So once we have this, then we will be able to continue the division process. In this case, negative 5x4 over x squared, we're gonna get negative 5x squared. And then we will multiply with the person who is doing the dividing yet again. Again, when you are doing all this multiplication, subtraction, etc., always check for the double negatives. They can get quite playful sometimes. Right, so you notice there's a double negative in the multiplication, which is going to create a double negative in the subtraction. We'll need to be careful to see when something actually produces a positive result in secret. Now we have 4x cubed divided by x squared. Clearly that's 4x. And then the cycle continues. And from here we have negative 2x squared divided by x squared, which is as simple as it gets. So in this case, we will conclude that 2x5 minus 7x4 plus 11x3 minus 11x squared plus 9x minus 10 is actually equal to, and then we will have the quotient, 2x cubed minus 5x squared plus 4x minus 2 multiplied by the person doing the dividing, x squared minus x plus 1 plus the remainder, which in this case is 3x minus 8. And we are done. Right, so moving on, we will go on to talk about identities briefly. For identities, all you need to know is that sometimes we will use the symbol congruent, which is this triple line equal sign. And whenever you have identities, because it literally means identical, you can simply compare coefficients. If I say that 3x squared is identical to px squared, it is a no-brainer that p equals to 3. So this will be the tactic you will be using. Of course, you can also substitute in random numbers of x in order to generate simultaneous equations after comparing coefficients. This could be helpful as well, and we have actually seen this in surds already in our previous video. So allow me to move on. I will leave the review of the contents here as an exercise for you to go through by yourself. Now, the next thing we need to talk about briefly is remainder theorem. Remainder theorem tells us that if I have any algebra who is a polynomial, fx, and I divide by ax plus b, then the remainder, right, which is the leftover from long division just now, the remainder is always the f of negative b over a. As a reminder, this does not mean multiplication. This simply means that x equals to negative b over a, and then we sub this into the algebra whose name is f. Right? Okay, let me take a look at that chat for a moment. Wow, is this 3 marks topic? So true, dude. So true. It's a topic that people tend to get scared of because they see all these long chains of algebra and it's like, you take a look at it and you're already tired. Fair enough, I sympathize. I'm tired too. It is past midnight right now. Look at that, the time, 12:01. But even if it looks bad, as long as you understand the mathematics and you know what you are doing, then you already have the faculties required to solve the problems. So there's no rational reason to be scared. Just go in, guns blazing, pants off, do your best, see what happens. Right, so I don't really have much to say for remainder theorem, and we will take a look at some examples of this later. Maybe for now, just to give you a taste of how problems might come about, let's take a look at example C on this page. It tells us that we have some polynomial x4 plus x3 plus 2x squared minus 14q4, and q is a rational number. It then tells us that, let me move this thing a little bit. It does not want to respond to my keyboard. Great. Okay, there we go. Right, it also tells us that the remainder is 1 minus 117q4 over 9. When dividing by x minus q, find the exact value. So in this case, what I will do is I will let fx be equal to the polynomial they have given me. Now, strictly speaking, this isn't necessary, but the good thing about introducing your own function notation is that we can immediately say f blah 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 instead of saying sub x equals to blah 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 into f. That doesn't feel nearly as lazy to do. Right? So in this case, we are dividing by x minus q. So ax plus b will be equal to x minus q. In this case, a equal to 1, b equal to negative q, and therefore negative b over a will be positive q. You can memorize negative b over a as the magic number that turns the person doing the dividing, in this case x minus q, that turns him into 0. In this case, if I want x minus q equal to 0, it is clear that the magic number will be x equals to q. So I'm going to take this magic number x equals to q and I'm going to sub it into fx. In other words, we will simply have fq. If this was a real life class and nobody was around to monitor it, I would refer to this as a vulgar phrase, but since we are doing this online, let us not do that. In this case, fq will give us the remainder, and the remainder has already been told to us. 1 minus 117 q4 whole thing over 9, like so. And of course, they have already given us the algebra for f, which is this funny person over here. So we can replace all of the x with q, which will give us q4 plus q3 plus 2q x squared, in this case q squared, minus 14 q4 equals to 1 minus 117 q4 over 9. Right, so this is what we will have. From here, we need to go on to find q. So let us try and simplify a little bit. Obviously, q and q squared will be q cubed. So it will combine with the q cubed in front, we'll get 3q cubed. The q4s will also simplify, we'll get minus 13q4. And in this case, we will have 1 over 9 minus, and then you will have 117 over 9. Now 117 over 9 conveniently is 13. So from here, we can simply cancel out the q4s, and this will give us q3 equals to, and then I'll move the 1/3 over, which will give us 1 over 9 divided by 3, in other words 1 over 27, which conveniently is 1/3 cubed, and therefore q equals to 1/3, and we are done. Now, similar to remainder theorem, something else that we also need to understand is the factor theorem. What if we do f negative b over a and we get 0? F negative b over a is supposed to give us the remainder. So if your remainder is 0, that will mean that perfect division has taken place. For example, 24 divided by 2, right? You're actually going to get a remainder of 0. And this makes sense because 24 divided by 2 is 12 exactly. So whenever you get perfect division, what would that mean? That means that the person doing the dividing, for example in this case 2, is a factor. And this makes sense. You learned this 2 years ago in Sec 1, that 2 is a factor of 24, because 24 divided by 2 gives no remainder. Over here it's the same thing. If the algebra that is doing the dividing, in this case ax plus b, is a factor, then remainder theorem actually gives us 0. And this will be the factor theorem instead. Again, we will be seeing this quite a lot in our later examples as well. So for now, let us simply demonstrate with a part 1 on this page. It tells us to prove that x cubed is a factor of this long guy. So in order for us to do that, we will simply let fx be equal to x cubed plus x squared minus 4x plus 6. From here, the magic number will be the person who turns the divider x plus 3 into 0. So the magic number will be negative 3. So let's take a look at f negative 3. You'll realize that you have actually negative 3 cubed plus negative 3 square minus 4, negative 3 plus 6. This will give us negative 27 plus 9 plus 12 plus 6. And if you work this out, you will realize it is equal to 0. So we conclude that x plus 3 is a factor of x cubed plus x squared minus 4x plus 6. I'm just going to short form and write fx. And we are done. Proven. Right? It's really that simple. Plug in the numbers, check with your calculator, wham, you're done. There's a reason why the proving itself will typically only be 1 mark. Having said that, however, there will be certain situations where the question doesn't ask you to prove the factor directly, but you're still going to have to do it as part of intermediate working. The most common situation where this happens will be cubic equations. So cubic equations are always solved with a 6-step method. Well, actually no, just a 5-step method. So step 1 is to always take a look at the original math problem, the cubic, and try and find a linear factor. Typically, this will involve guess and check, but since you have a scientific calculator with you, you can simply press the math problem into the calculator and then figure out what the answers are. Then you can retroactively find the factor. So if we're doing guess and check, what we will do is we will sub in random numbers and we will observe, hey, when I use a magic number, for example -1, I get 0. And therefore, I will use factor theorem to say that x plus 1 will be a factor of fx. Why do we know it is x plus 1? Simple. If you remember, the number that goes into f is the magic number that turns the bracket into 0. Which means that if I have the bracket, then I can find the magic number. If I have the magic number, then I can recreate the bracket. In this case, the magic number is -1, which means that we need a bracket that turns into 0 when we sub in -1. And clearly that will simply be x plus 1. Now, once you find the first factor, the second step is to do long division by yourself and change the cubic into the person that you found, the linear, multiplied by a quadratic. Right? So in this case, I will take this guy, I will do long division with x plus 1, and this will give me a quotient of x squared minus 8x plus 12. Now, if you don't want to do long division, another method you can do is, because you already know it is a quadratic, you can simply say that fx is equal to the person you found x plus 1 multiplied by a random quadratic. This will turn into a polynomial identity. And then you can use comparing coefficients, just like surds. But be advised that the amount of work is still very long. It's not necessarily easier than long division. In fact, long division might be better because you can do the long division with your bad handwriting and treat it as rough working. Whereas for identities, you need to write every single step you take down on your actual answer paper, which you might not be able to afford to, because you must remember that in your syllabus, you're doing the work on the question paper. Once you have obtained the quadratic, the next step will simply be to go on to factorize the quadratic if possible. If not, then you're going to have to use quadratic formula. If that doesn't work, it probably means the discriminant is less than 0 and there's no solution. So in this case, we see that we do long division to get this guy. I will then do factoring to get that guy. And therefore, the original math question is equal to 0. We will replace it with this factorization. So this factorization equal to 0. And from here, if you remember the first video we ever saw, we will do 0 product property and split the brackets up into x plus 1 equal to 0, x minus 2 equal to 0, and x minus 6 equal to 0. From here, we will have the 3 solutions. Always remember, because the second guy is a quadratic, it's possible for him to have 1 distinct real root or 2 distinct real roots, depending on the discriminant. Right? So take a look at this point. You will sometimes need to check the discriminant, because some questions don't care about the answers. They just want you to see how many solutions there are, how many distinct real roots there are. Having said that, however, we don't only have a quadratic, we also have a linear on the obtained from the guess and check step. So that linear portion will always give you at least 1 solution in the overall question. So it's not as bad as quadratics, where you might sometimes get no real roots and then we are done. Now the last thing we need to know is partial fractions. Now partial fractions means that when I have a long fraction of polynomial divided by polynomial, I can take a look at what is inside the denominator and then split the original entire fraction up into smaller pieces of fractions. If the denominator has a linear person, its piece will be like that. If the denominator has a linear person square, its piece will actually be 2 separate pieces. The first one will not have the square on the denominator, the second one will have the square. Last but not least, if the denominator contains an x square that cannot be factorized, we will copy the entire thing over, and the numerator will be ax plus b. In this case, all these a's and all these b's will all be constant real numbers. And some examples have been given on the right hand side of the table, so I will leave you to look at that yourself. Without further ado, I will go on to talk about the strategy. In order for us to do these kinds of questions, we need to first of all recognize that partial fractions only works if the fact fraction is already in simplest form. If the division actually works, for example, I have 2x cubed plus x divided by x squared plus 1. Now, if you look at this carefully, the division actually works. The numerator is x cubed, denominator is x squared. Division is definitely possible. It will be ugly, yes, but it is possible, because it's degree 3 divided by degree 2. X cubed over x squared gives me x. When this happens and the degree on top is bigger than the degree below, we call it an improper fraction. If the fraction is improper, you must use long division to split the quotient from the remainder. The quotient will be by himself without a denominator, and then the remainder will have the actual denominator stuck onto him. Again, I bring you back to the example of 7 divided by 3. We know it's 2 remainder 1. And therefore, 7, which is too big, will be split into the quotient 2 plus the remainder 1 divided by the original dividing person 3. And then this guy over here will no longer be improper. Then we can do partial fractions. And the number 2, the quotient, we will leave him alone. He can just stand there. The second thing we need to know is how to actually find the constants capital A, capital B, etc. In order to find these constants, what we will do is we will actually create a polynomial identity. So looking at this example over here, part 1 tells us, can we factorize the cubic into this guy? So what we will do is, I will let fx be equal to the cubic, and we will do guess and check and observe that f2 is equal to 0. The magic number is 2, therefore the dividing person is x minus 2. So it will be a factor by factor theorem. From here, I will do long division, and I will get the quadratic x squared minus 4. This is very nice because it is equal to x squared minus 2 squared. And in sec 2, we learned that x squared minus 2 squared will simply turn into x plus 2, x minus 2. From here, we can combine the x minus 2 together, and this gives us the final result as desired. So more interestingly, we will move on to the partial fraction portion. They want us to do partial fractions of x squared minus 8x plus 44 divided by the same person in part 1. In other words, this is equivalent to saying x squared minus 8x plus 44 divided by x minus 2 square x plus 2. And from here, what we will see is that this guy over here is a repeated linear fraction. Repeated linear factor. And therefore, he was split into, if you remember the formulas from just now, 2 pieces, like this. The first piece, right, will have no square. The second piece will have the square. After that, we have a regular linear factor, x plus 2, and he will simply, based on the formulas we saw last page, he will simply be a number divided by x plus 2. Somewhat straightforward. This one is nothing scary. So once we have created the formula, what we're going to do is we will multiply both the left and right hand side by the denominator of the original math problem. What this means is that the left hand side will lose the denominator, correct? So I will multiply by x cubed minus 2x squared minus 4x plus 8. Alternatively, this is equivalent to saying multiply by x minus 2 squared x plus 2. So the denominator here gets cancelled out. We're left with the numerator. And as for the right hand side, because I am multiplying by this whole thing, what we see is that the denominators get cancelled out and there will be some leftovers. So that will be something to take note of as well. Right, so up to this point, one thing I need to point out to you really quickly is that if you if you look carefully over here, there's actually a bit of a typo, right? I need you to take note. So in this case, I think you might have noticed already, but this person here is incorrect. What we have right now is a over x minus 2 plus b over x minus 2 square, right? And then afterwards plus c over x plus 2. And this whole thing is multiplied by the denominator, which is the answer from part 1, x minus 2 squared x plus 2. So in this case, what we will see is that the a undergoes cancellation, like that, to get a x minus 2 x plus 2. The b is a little more straightforward. It just cancels out this whole thing, leaving behind x plus 2. Last but not least, the c cancels out the x plus 2, leaving behind this whole chunk over here, which will be x minus 2 squared. Right, so definitely some cock up happened in the coordination of the capital letters here. What we will see is this result. Right? So from here, what we will do is, let me move the screen a little bit. After doing the multiplication, we should get the following. X squared minus 8x plus 44 equals to, and then I will write in what I wrote just now. Like this. Now once I have this thing out, this will become a polynomial identity. Since it is a polynomial identity, then we can go on to solve it by substituting numbers, or we can solve it by comparing coefficients. Now, comparing coefficients is again the slower and clumsier method. So instead of that, what we will do is we will sub in some magic numbers. In this case, we notice that if x is 2, the left hand side will give us, let's see, 4 minus 16 plus 44, we're going to get 32. And what happens on the right hand side? You will see that I have a 2 minus 2, 2 plus 2. 2 minus 2 here is equal to 0, so the whole thing is equal to 0. Right? And the same phenomenon happens for c as well, because it turns into c 2 minus 2 squared, which is c times 0 squared, which is 0. In other words, by choosing appropriate magic numbers to sub into x that can turn the brackets on the right hand side into 0, you can eliminate some capital letters. In this case, a and c will be eliminated, and this leaves us with b 2 plus 2. In other words, 4b. From here, it is clear that b equals to 8. The other magic number, as you might have noticed, is negative 2. And in this case, the negative 2 will also produce a cancelling effect. So in this particular situation, the cancelling effect will attack a and b instead, correct? We will see that the left hand side turns into negative 2 square minus 8 multiplied by negative 2 plus 44, which is 64, no problem. The right hand side over here, we're going to see a, negative 2 minus 2, no problem. Negative 2 plus 2, big problem. This is equal to 0, whole thing equal to 0. So again, a is cancelled. And this time round, as said earlier, we will see that b also gets cancelled because you have x plus 2, right? So if x turns into minus 2, we will have b times 0, which is 0. So in this case, we have eliminated a and b, and this is useful. We have already found b anyway. So let's eliminate a and b, and there afterwards, we will be left with c, negative 2 minus 2 squared, which is clearly going to be 16c. Like so. Once you have this, then you can simply move the 16 over. You're going to get c equals to 4. Once you are done with this, there is no other situation where we can do any elimination of the capital letters. So use a number you like. For me, I typically use 0, positive 1, or negative 1. You can use any number at this point because there's only one unknown left, capital A. So no matter what number you use, you're going to win. There's only one unknown. So I'm going to use 0. I'm going to get 44 equals to A, which is A, 0 minus 2, 0 plus 2, plus B, which is 8, 0 plus 2, plus C, which is, let's see, which is 4, and then I'll have 0 minus 2, whole thing squared. This will then simplify into negative 4A and then plus 8 times 2, 16, plus 4 times 2 squared, which is 4 times 4, which is 16. So I'll have plus 16 plus 16. In other words, I will have plus 32. Right? Once you have this, then it is deducible that A is equal to minus 3. Now that we have A and we have B and we have C, then we can write our final answer. So we shall go back to the original intention of the math problem, which is to do partial fractions. Now that we have found A and B and C, we can answer directly to the question. I believe you will remember what I mentioned in the previous few videos. Doing math papers is a bit like customer service. You always want to serve up whatever they ask for. Very similar to your English comprehension as well. So what they asked for is the partial fraction of x squared minus 8x plus 44 divided by x cubed minus 2x squared minus 4x plus 8. So we will do exactly that. We will solve them exactly this. looking at our A, our B, and our C, what we have is negative 3 over x minus 2, right, plus, and then B is 8, so plus 8 over x minus 2 square, plus C is 4 over x plus 2. And this whole thing will be the final answer. So we have turned something that looks extremely impossible and impolite into 3 smaller pieces. This will be particularly helpful for those of you moving on to Sec 4 next year, where we will have to do partial fractions in order to turn an impossible math problem into something that at least looks a little more reasonable. So there is another example over here, which I shall go through with a little less detail. Over here, they tell us to express in partial fractions again. This time round, we see that it is a little more interesting because the denominator has x squared plus 5, which we cannot simplify. So over here, we're simply going to get the standard linear factor plus an irreducible quadratic factor. If you remember, this will give you a linear on top. Oh, why am I writing 5? It will simply give you a linear on top like this. And therefore, I will multiply left and right by the denominator. This will give me a x squared plus 5 plus bx plus c x minus 1. From here, I think it is clear that the first magic number is 1. This will give us 12 equals to a 1 squared plus 5 plus, and then over here, because there's an x minus 1 on the bracket, it turns into 0, right? I'll get 1 minus 1. Now this very clearly gives me 6a, implying a equals to 2. The next magic number is a little harder to spot. We will choose 0. Why do we choose 0? Because over here, there is a bx. So if x equals to 0, very obviously bx is equal to 0 as well. So what we will do is, I will choose x equals to 0, left hand side will be 6, right hand side, oh, the color changed, oh well, it's fine. The right hand side will be a little bit more ugly than the previous question. This time round, we know that a is equal to 2, so I'll have a x squared plus 5, like this, which clearly gives us 10. And then bx plus c, the x is equal to 0, bx will completely disappear, so I'll just have c, and then x minus 1, which in other words will simply be negative c, like this. From here, it is deducible that c equals to 4. And now that we have found two things, we don't really have any magic numbers left in this scenario, so let us use any number we want. So for me, I'm going to deliberately choose negative 1, and therefore the left hand side here, right, is going to give us negative 1 squared plus 5 negative 1 plus 6, and this works out to be 2. From here, then we will do the same thing as before. I'll plug in the capital A, capital B, capital A, capital C, and then I will plug in x equals to negative 1. So in this case, we should get 12 plus 4 minus b multiplied by negative 2. Clearly, this gives us 12 minus 8 plus 2b. In other words, 4 plus 2b, which implies b is equal to negative 1. From here, we will be able to come up with our ultimate conclusion, which is that the very big and scary x squared plus 5x plus 6 divided by x minus 1 multiplied by x squared plus 5 will simply give us a over x minus 1 plus bx plus c over x squared plus 5. If you want to be OCD, you can swap these two around and make it look a little nicer, 4 minus x squared. This is completely fine. And this whole thing will be our final answer. Now, for the second problem is actually a lot more enlightening. If you look at problem 2b, you might notice a serious issue, which is that the numerator has the linear x plus 1 multiplied by the cubic x3 plus 2. In other words, it will be degree 4 on the numerator. This is a disaster because the denominator is x squared multiplied by a linear 2x minus 3. In other words, the denominator is degree 3. So we have degree 4 over 3. This is actually improper. So before we do anything, let us start by attempting to simplify this person over here. Ignore the minus there. Right, we're going to start with this, and we're going to open up all the brackets. This will give us 3x4 plus 3x3 minus 6x minus 6, whole thing divided by 2x cubed minus 3x squared. From here, what we're going to do is we will have to do long division, which we saw earlier, in order to find what the quotient is, find what the remainder is. So this long division will be a little bit ugly. I will write down the process for you, and you can review it in your own time. Have a look. We start with the numerator we found earlier. And then we divide by the denominator we found earlier. Alright. Whenever you have a case where one of the terms is skipped, in this case x squared is skipped in the numerator, please also make sure to include a 0 over there, right? If you remember just now, we expanded to get this. Okay, I'll write it down one more time. After this, I'm erasing it for good. You notice that we skipped. We went from x4 to x3 to x1. So if you have a skip, in order to make your life a little easier when you do the subtraction, you should put in a 0 as a placeholder, so that the horizontal space is available for you when you do subtraction later. Otherwise, you're going to have to mental sums everything. So over here, we will divide as follows. Right, always look at the first term. Multiply by the person doing the dividing. Subtract after doing the multiply. And then from here you can carry on. Very quickly you'll see why this particular long division is nasty. We actually have fractions thrown into the mix here. Unfortunately, this is something that you will simply have to get used to. And we are done. From here, then we understand, okay, now I have the quotient and I have the remainder, right? I'm going to write these on top for reference purposes. And now that we actually have found the quotient and the remainder, then we can go on to actually do our partial fractions process. So in this case, with our quotient and remainder set, we will simply focus our attentions on the remainder portion. How do we do that? We will start by telling the teacher who is marking that, okay, look, this is your ugly boy, 3x plus 1 x cubed minus 2 over x squared 2x minus 3. This guy, I know he is equal to the quotient 3 over 2x plus 15 over 4 plus the remainder, which is this really impolite quadratic divided by the original denominator. Like so. From here, then I will take this guy and we will do our actual partial fractions. So the steps will be the same as always. We will let this guy be equal to, and then from here we will plug in the partial fractions formulas from earlier. So in this case, the partial fractions formula will start with an x squared. This is actually a repeated linear factor, right? If we imagine ax plus b with a equal to 1 and b equal to 0, then it will simply give us x. But because this is a linear with a square on it, it means that it is a repeated linear factor. So we will split into two pieces. The first piece will be a constant over x without the square. Second piece will be a constant over x with the square. Afterwards, there's one other thing in the denominator, which is 2x minus 3. So we will use the standard linear factor formula. Right? So once we have this, similar to all the other problems before us, we will multiply both the left and right hand side by the denominator, and this will create for us a nice, okay, not so nice, but it will create for us a polynomial identity. Oh, I made a mistake. Like so. From here, then we will return to our usual patterns, return to our 老样子, and perform some magic number substitution. In this case, probably the easiest one is x equals to 0. We shall get negative 6 to be equal to 0 plus b, 0 minus 3, yes, plus 0. In other words, this will give us negative 3b, from which it is easily deduced that b equals to 2. Once you have this, it is also easy for us to move on to x equals to 3 over 2. And this will give me 165 over 16 equals to, let's see, 0 plus 0 plus c 3 over 2 square, which is equal to 9 over 4 c. Clearly this means that c will be equal to 165 over 16 divided by 9 over 4, which gives us 55 over 12. Once you have these, we are out of magic numbers, so you can choose any number you like. As before, I like negative 1, 0, 1. I'm going to use 1 over here, and we're going to get on the left hand side negative 3/4, a bit weird, but okay. On the right hand side, we're going to get a multiplied by 1, multiplied by 2 times 1, which is just like this, minus 3. And then our plus b, which will be 2 times 1 minus 3. And our plus c, which is 1 squared. Conveniently, we have already found c, which is 55 over 12. And we have also found b, which is 2. Simplifying this will then give us a total of, let's see, should give us negative a minus 2 plus 55 over 12. So negative 3 over 4 equals to this whole mess. Simplify this whole mess, you'll get a equals to 10 over 3. Once we have found the required numbers, right, then we are ready to write the final answer out. If you remember, the final answer, the partial fractions, must be equal to the original math problem. And therefore, that means that we will actually need to include the quotient we found at the very beginning as well. That's why this problem is so long, right? It's 6 entire marks. So in this case, what we will see, allow me to clear the space a little bit, what we will see is that the original math problem, which is the ugly fraction, right? We will write him as the following situation. Let me activate the pen. We will write that we will do all that work and we will conclude that the original math problem, 3x plus 1 x cubed minus 2 divided by x squared, 2x minus 3, this original math problem will actually be equal to our quotient, 3 over 2x plus 15 over 4, plus the remainder, right? So right now, up to this point, it is actually the wrong thing. Up to this point, it's exactly the same. This is the quotient, this is the quotient. And then this is the remainder, this is the remainder. But we have already found that the remainder can be split into this, the partial fractions. And we have found A, B, C. So from here, I will simply plug in the corresponding numbers, plus A, which is 10 over 3, over x, plus B, which is 2 over x squared, plus C, which is 55 over 12, over 2x minus 3. So we have performed a 1-for-1 replacement like so. Of course, if you have a fraction stacked on the numerator, it looks a bit ugly. So you can always move the denominator down and let it join the overall denominator. For example, in this case, if I have, let's say, let me write it in the middle over here. If I have 10 over 3 whole thing over x, it is simply 10 divided by 3 divided by x. And from here, it is easy to simplify this into 10 divided by 3x. Similarly, over here, we can have 55 divided by 12 multiplied by the entire 2x minus 3. And this whole thing over here will be my final answer. This will be the partial fractions. Alright, now let me take a swig of water and then we will move on to a few more practice problems about remainder theorem, factor theorem, and cubic equations. And then we will be done for the day. For now, you can look at this. Okay, let us continue. Before we really continue, however, let me just say that the next few problems we're going through are all related to factor theorem, remainder theorem, cubic equations, all that. So for those of you who are already confident in this topic, we are actually just about time for the day. So if you are already familiar with the topic and you think you are fine, there is no need for you to stay. You can actually stop over here. We are done with the raw content for the day. For those of you who would like to stick with me and review some worked exercises, then let us move on. Or rather, let me move on after I put on my half glove. I need the glove so that it doesn't affect with the writing tablet. Okay, so let us move on. As a reminder, polynomials require real numbers. Okay, so for now, there are a few problems that I would like to tackle actually. We will start with, let me get rid of this. Bye-bye. We will start with a question about identities and the remainder theorem. Let's take a look at question 4 over here. So this problem over here is an exercise in remainder theorem and in polynomial identities. They tell us that we have some algebra which is fx equals to x cubed minus 6x squared plus ax plus b. In this case, a and b are real constants, and they tell us it is exactly divisible by x minus 3 and that it leaves a remainder of negative 55 when we divide by x plus 2. Very interesting. So over here, let me group them by color. We have exactly divisible by x minus 3, and then we have remainder of minus 55 when divided by x plus 2. The question wants us to find a and b first of all. This is actually very straightforward. If it is exactly divisible by x plus 3, then that means that f3 will simply be equal to 0 by the factor theorem. Why do we substitute in 3? If you remember, it is because we substitute in the magic number that turns the dividing person into 0. So of course, we're putting in 3. Having said that, putting in 3 will give us 27 minus, let's see, 6 times 3 times 3. Ooh, that's a big one. Minus 54 plus 3a plus b equal to 0. And this part over here clearly implies that we are actually able to rearrange the terms. And from here, we can create simultaneous. For example, you could choose to do b equals to 27 minus 3a. Let's call this equation 1. Next, we will look at the green colored portion. They tell us that if we are dividing by x plus 2, we get a remainder of minus 55. So the dividing person is x plus 2. If we want him to be equal to 0, x equals to negative 2. And therefore, we will substitute in the magic number, negative 2. From here, by remainder theorem, what we will see is that I will be equal to the remainder minus 55. So let us sub in negative 2. We're going to get negative 8 minus, let's see, 6 times positive 4 minus 24 minus 2a plus b equals to negative 55. So from here, we can actually go on to, let's see, how will this even be simplified? This is a bit dirty. We will change this to the following. b minus 2a minus 32. And then from here, we will go on to say that a is equal to half b plus 23 over 2. Let's call this equation 2. From here, then it becomes simple simultaneous equations. I will substitute number 1. Why did I write sub again? I will substitute number 1 into number 2. And this will give us a equals to half b plus 23 over 2. This simplifies over here into a equals to 10. Then we will sub this a equals to 10 into number 1. And b will be equal to 27 minus 3a. And this gives us negative 3. So we have a equals to positive 10, b equals to negative 3. And we are done. Right? So the next thing will then be to find the roots of fx equals to 0. If you remember this from 2 videos ago, when we say roots, it's really just a nice way of saying the solution to the math problem, right? I will set it to be equal to 0. I will find the solution. So in this case, now we know that fx is equal to x cubed minus 6x squared plus ax plus b, which is plus negative 3. So I'll just write minus 3. We also know that x minus 3 is exactly, or rather, exactly divides fx. In other words, it is a factor. As a result, it will be simple for us to perform long division over here, divide by x minus 3, and this will eventually tell us how to factorize out the entire fx. Over here, the long division process, please revise this if you are having trouble keeping up, because we will not spend further time reviewing the process, right? So over here, this long division process will give us the following scenario. Like so. And therefore, I will conclude that we have x minus 3 multiplied by the entire quadratic x squared minus 3x plus 1. Like this. Now, once you have this thing over here, then you will see that very clearly we have a linear and we have a quadratic right? So if you have a linear and you have a quadratic, then it is simple enough for us to solve the problem. We can use the zero sum property to split it up, and then we can solve the quadratic separately by himself. So in this case, we have fx to be equal to 0. By the zero sum property, we have the linear equal to 0 or the quadratic equal to 0. So in this case, the linear equal to 0 clearly gives us x equals to 3. The quadratic equals to 0 is a little uglier. We're going to have to use the quadratic formula. And once you do the quadratic formula, you should get, let's see, 3 squared, 9, 9 minus 4, 5. So we shall have the following. And therefore, we have 3 different answers. 3 minus root 5 over 2, 3 plus root 5 over 2. And we are done. Right, now the next 2 problems are also somewhat on the straightforward side. Question 7 wants us to find the number of distinct real roots. So they didn't actually ask you to find the value of x. They just want to know how many solutions there are to the math problem. Depending on the situation you get, you might actually be able to use the discriminant here. But if I'm being honest, I don't really recommend it. You can still just solve for x normally. And obviously, if you solve for 3 values of x, then there's 3 solutions. So for question 7, what we will do is, step 1, let us introduce function notation. We will let fx be equal to the person they gave us. Right, and this guy will be equal to 0. So over here, what we will do is, we are going to pretend to do guess and check. I say do guess and check, but in reality, you can use your scientific calculator, correct? You will observe that when I use x equals to minus 4, we're actually going to get 0. And since f of negative 4 is equal to 0, we conclude that x plus 4 is a factor of fx. Now in reality, there are other numbers you can use. For example, you can actually use x equals to half as well. That's completely fine. From here, what we will do next is we will have to do long division. Again, I will be doing the long division by myself without going through the steps, so please review back to the earlier part of the video if you have trouble following along. Let's see how fast I can do this, since we're going mental sums, right? I might as well challenge myself a little. I think I went pretty fast just now. Hopefully I can go fast over here as well. Right, and we're done. We're going to get x plus 4, 2x squared plus 7x minus 4. And over here, the quadratic, conveniently, can actually be factorized even further. We're actually going to get 2x minus 1, x plus 4. From here, we can simply combine the x plus 4's together. And then we say that this fx is equal to 0. So if you look at this part over here, it becomes very clear that we have 2 distinct real roots. There are 2 solutions, which are negative 4 and positive half. And we are done. Alright? So the last problem is also very similar. We have over here, let's see, show that x minus 1 is a factor, so that will be factor theorem. Afterwards, find the roots, and that will be basically the same thing as question 4 part 2 and question 7, where we do long division, and then afterwards we do zero product property. So question 8, show that x minus 1 is a factor. In this case, we don't even have to pretend to do guessing. They already told us it's x minus 1. So the magic number will be positive 1. So step 1, let us create the function notation. Let fx equals to x cubed minus 2x squared minus 5x plus 6. Once we have this, I will say that since f1 equals to 0, we conclude that x minus 1 is a factor of x cubed blah 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 blah, right? And this is what they wanted us to show in the first place. Shown. If you want to show off and you are a math teacher, then you can just use QED. Unfortunately, if you're viewing this, you're probably not a math teacher, so too bad, right? Shown. Once we have this, then we can go on to say that fx will be equal to, and then over here, just like the other two problems, we are going to have to do long division in order to find the quadratic portion. Of course, again, if you want to do polynomial identities by saying that x minus 1 is equal to ax squared plus bx plus c, and then you open up the brackets or you substitute in magic numbers to find a, b, c, that is also fine. The problem is that means that you are finding a, b, c in a question about finding x. So you have went from 1 unknown to 4 unknowns, which feels like S. Whereas if you're doing long division, all you need to do is to memorize the steps, and boom, you're done. Same as before, I will be going through this as fast as possible, so please try to keep up. Right, in this case we will have x minus 1, x squared minus x minus 6, and over here conveniently this person, I think he can be factorized. Let me take a look. Yes, he can. Sometimes I need to like stop for a moment because I'm doing all this mentally, yeah? So if we factorize this, you will realize that unlike the previous problem, we actually get some pretty nice results. We will have x plus 2, let's see, x minus 3, like so. Right, unlike 4 part 2, where you couldn't factorize and you had to use the formula, which was ugly, and 7, where we could factorize, but the factorization gave us repeated linear, and therefore there were only 2 distinct real roots. This time around it's very nice. This whole thing will be equal to 0, right? So looking at this rainbow portion, looking at this whole rainbow portion, we will conclude that x is equal to positive 1, negative 2, or positive 3 by using the zero sum property, and we are done. Surprisingly straightforward for 5 marks, but that just means it is all the better for you. Alright, so up to this point, this will be all the content that I have to cover for today. So if you have nothing else for me, I have nothing else for you. You are dismissed. I wasn't expecting so many viewers today, to be honest, considering the awkward timing. It is fitting neither to my local audiences nor to my overseas audiences. So I am very pleasantly surprised by the reception. Thanks for watching. Alright, ladies and gentlemen, we are done for today. I will be ending the stream soon because I actually have some personal affairs for today and tomorrow, so I am very exhausted. I do not want to stay online doing math for too long. Right? I think my maximum maybe will be 3 hours. Right now we are 1 hour 20 minutes in. I would not like to waste the rest of my energy. Alright, so let me see if there are any questions in the chat. No questions in the chat today. Alright, I guess the previous topic was just more interesting, right? Recurring surds counting to infinity. Whereas over here we simply have polynomials. It is very technical in nature. But for the students who are still watching at this point, I don't know why you are, but if you're watching at this point, I hope that you will take all the methods here to heart, because they will be instrumental in ensuring that when we move on to calculus next year, you have an easier time. Alright, so we're done for today. Okay, I will be ending the stream over here. Once again, ladies and gentlemen, thank you for your time, and I will see you in the next video. In the next video, we are going to move on to revisit a little bit about what we touched at the start. So far, what we have studied are quadratics, and we moved on to studying the quadratic problems themselves. We moved on to study square roots, the opposite of quadratics. Now we are expanding to higher powers, right? We have power 3, power 4, partial fractions, cubic equations. So naturally, the next step forward will be the study of powers in general, exponents, and correspondingly we will also study logarithms. We will then round off the study of powers with an introduction to binomial theorem. And from there, we will be done with the algebra segment of our Sec 3A Math syllabus. Alright, thank you for watching and take care. I will see you in the next video.